Hello everyone, my name is Sahil Saurabh Jain and this is my video on how to minimize a DFA for the course Automata, Theory and Computability. Let's look at what we will be learning in this video presentation. First, we have an introduction to automata. Next, we have what are finite automatas. Then we move on to DFA. We need to understand what a DFA is so that we can properly minimize it. Then comes a main issue for this presentation, that is the minimization of DFA, followed by the reasons we do it, the methodology, and we end off with an example so that we can better understand and learn. So, what is automata? Automata is the study of abstract machines and the computation problems that can be solved using these machines. Now, before we understand what a DFA is, we need to understand what a finite state machine or a finite automata is. Finite state machines are those machines that take a symbol string as input and modify its state accordingly. When the desired symbol is found, the transition takes place. The automata can either advance to the next state or remain in the same state during transition. Finite state machines have two states, that is, accept and reject. We can also represent finite state machines using phi tuples. The first one is Q, which is used to represent the finite set of states. Next we have sigma, which is used to represent finite set of input symbols. Then we have Q naught, which we use to define the initial state. Moving on, we have F, that we use to represent the final state. And lastly, we have delta, which is the transition function. Now, finite state machines have two divisions, that is finite automata with output and finite automata without output. For this video, we'll be looking at finite automata without output, as it has a subdivision into deterministic finite automata and non-deterministic finite automata, the latter being our aim for this video. So, why do we call finite state machines deterministic? We call them deterministic as for each input symbol, we can determine the state to which the machine will move. Also, these machines have a finite number of states, hence the finite in the finite deterministic automata. It is important to note that DFA does not accept the null move. That is, DFA cannot change state without any input character. Here is an example of DFA. We can see this DFA has three states, being A, B, and the final state. And for each state, all the transitions are complete. That is, when we get the input of 0, A state goes back to itself. And when we get the input of 1, A state moves to B. Same for B, as when B state gets the input 0, it moves on to the final state. And when it gets the input of 1, it goes back to A state. Same can be said for the final state, as when the final state gets the input 0, it moves back to the B state, and when it gets the input 1, it stays on itself. So what is minimization of DFA? DFA minimization stands for converting a given DFA to its equivalent DFA with minimum number of states. DFA minimization is also called as optimization of DFA and uses the partitioning algorithm. The reason for minimizing the number of states in DFA is to reduce its complexity to understand. We get large DFAs when we convert an NFA to a DFA. As we saw, NFA and DFA were part of finite automata. There is also the fact that all DFAs are NFAs, but not all NFAs are DFAs. So when we convert an NFA into a DFA, we get large number of states. For example, when an NFA has n states, a DFA can have up to the power of n states, hence causing a lot of complexity to understand. Here is the methodology of converting an DFA and minimizing it. The first step is that we have to eliminate all the dead states and the inaccessible states from the given DFA. The next step is to draw a state transition table for the given DFA, meaning the DFA without all the dead states and inaccessible states. Moving on to the third step, we take a counter variable k and initialize it with the value of 0. We then divide Q, that is the set of states, into two sets such that one set contains all the non-final states and the other set contains all the final states. This partitioning is called P0, that is the first partitioning. The step 4 is incrementing k by 1, finding pk for partitioning the different sets of pk minus 1. In each set of pk minus 1, we consider all the possibility pairs of states within each set, and if two states are distinguishable, we partition them into different sets in pk. In step 5, we repeat step 4 until no change in partitioning occurs, that is pk, that is partitioning k, is equal to the previous partitioning. In step 6, we club all the states in the same set into a single state. Let's look at this example to better understand what we just talked about. So here we have a DFA and we have to minimize it. So for step 1, we have to find a state that isn't connected to the initial state, that is Q0. So let's take a look at Q1. We can see that Q1 is directly accessible from Q0. So that's out of the picture. Next, we move on to Q2, which is also accessible from Q0 directly. Then we have Q3, which we can access through Q1, which is in turn connected to Q0. Moving on to Q4, we see that Q4 is connected to Q2, which in turn is connected to Q0. Next, we have Q5. Here we can see that Q5 isn't connected to any other state. That's why we remove it in step 1, hence eliminating it from the DFA. Here we can look at the DFA we get after removing the state Q5. The next step is to draw a state transition table. That is, we have to map all the states with the inputs we get and which state will be the output. For example, Q0 on the input 0 goes to Q1 and on the input 1 goes to Q2. For Q1 on the input 0 we move on to Q2 and for the input 1 we move on to Q3 and henceforth. You can see we have an arrow marking the initial state and stars marking the final states. In step 3, we use the equivalence theorem, that is, we make our first partitioning. We can see here that we have divided all the final sets and all the non-final states into two sets, that is S1 and S2. S1 containing all the non-final states and S2 containing all the final states. Let's take S1 and try to partition it further. For the first partitioning, we choose Q0 and Q1 state. Q0 on the input of 0 moves on to Q1 state, and Q1 on the input of 0 moves on to Q2 state. We can see that Q1 and Q2 belong to the same set. That's why we keep it as it is. Moving on, we see that Q0 on an input of 1 moves on to the Q2 state, and Q1 on the input of 1 moves on to the Q3 state. Here, Q2 and Q3 do not lie in the same set. So we can partition Q1 and Q0 into different sets. But there still remains Q2, and we have to find out whether it will be in a state set with Q1 or with Q2. So let's choose Q1 and Q2 next. Q1 on the input of 0 goes to the Q2 state, and Q2 on the input of 0 goes to the Q2 state. Hence, they both go to the same state, and there's that. Moving on, for the input of 1, Q1 goes to the Q3 state and Q2 goes to the Q4 state. That is, they both go on to states that are in the same set. So Q1 and Q2 will remain in the same set, whereas Q0 will get its different set. Shown here that S1, we have three sets now, that is Q1, Q2, set 2 with Q2, Q3, and set 3 with Q0. In step now, let's try to partition S2. There are only two states in S2 with Q3 and Q4. Q3 on the input of 0 moves on to Q3, and Q4 on the input of 0 moves on to Q4. That is, they both move on to sets in the same states in the same set. Q3 on the input of 1 moves on to Q3, and Q4 on the input of 1 moves on to Q4. Again, these both states move on to states in the same set. So they both will remain in the same set. Finally, we keep repeating step 4 until no change in partitioning occurs. As we can see, for the partitioning 1, we have Q3 sets, each with first with elements Q1, Q2, second with elements Q3, Q4, and third with elements Q0. We then repeat these steps we just did for the partitioning 2, and we again get 3 sets. That is the first set with Q1, Q2, second set with Q3, Q4, and third set with Q0. Now, as the both partitionings are equal, we stop our repetitive process over here. Now is the time for the final step. We combine or club all the states of each set into one single state. That is, Q2, Q1 will become one state, Q3, Q4 will become one state, and Q0 will become one state. Here we can see the final DFA. That is, when Q0 gets the input 0 or 1, it moves on to state Q1, Q2. When Q1, Q2 gets the input 0, it comes back to itself, and when it gets the input 1, it moves on to the final state Q3 and Q4. Q3, Q4 on both the inputs, that is 0 and 1, come back to themselves. We can then condense these, like by assigning Q0 the symbol A, Q1, Q2 the symbol B, and Q3, Q4 the symbol C. With this, I would like to end my video presentation on minimizing DFAs. Thank you for watching.